In this video, you will see complementary topics on equations for planes, such as intersecting planes and distance problems involving planes. As always on this channel, you can expect a clear and concise explanation of each topic. Before starting, you should know how to write equations for planes in three-dimensional space. If you have any questions about equations for planes, you should watch the video that appears in the upper right corner of the screen before proceeding. Please don't forget to click on the like button, subscribe to our channel, and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. Let's start the video by discussing the relative position between planes. When we describe the relationship between two planes in space, two planes can have one of the three relationships. They can be parallel, coincident, or intersecting. Two planes is called coincident planes when they lie exactly on top of each other. You cannot see both of them at the same time because they're on top of each other, and their equations are exactly the same. Now let's move these two parallel planes apart. When two planes are parallel, their normal vectors are parallel as well. This implies that the normal vectors must be scalar multiples of each other. The next figure depicts two intersecting planes. Let's start with two parallel planes and then rotate one of them as shown in the figure. The normal will rotate just as the plane. Let the angle between the two planes be theta and the angle between the two normal vectors be alpha. In the figure, there's a quadrilateral, and we know that the sum of the interior angles of any quadrilateral is 260 degrees. We add all known interior angles and subtract the angle sum from 360 degrees. We can see that the alpha angle is equal to the theta angle, and therefore the angle between the planes is equal to the angle between their normal vectors. Since the angle between the normal vectors is equal to the angle between two planes, we use the dot product of the normal vectors to find the angle between them. The angle between two planes is calculated with the knowledge of angle between their normal vectors. In other words, the angle between normal to two planes is the angle between the two planes. Now let's summarize our discussion as follows. If vectors n1 and n2 are normal to two intersecting planes, then the angle theta between the normal vectors is equal to the angle between the two planes, and theta is given as follows. Consequently, two planes with normal vectors n1 and n2 are perpendicular when n1 dot n2 equals 0. Parallel when n1 is a scalar multiple of n2. Determine whether the planes are parallel, perpendicular, or neither. If neither, find the measure of the angle between them. First of all, we need the normal vectors. The coefficients of x, y, and z are the components of normal vectors to the planes. So the normal vectors for these planes have components. 1 minus 4, 2, 2 minus 8, 4, and we can see these two vectors are scalar multiples of each other. The normal vectors are parallel, so the planes are parallel. The procedure to solve part B is the same. We find the normal vectors first. The given equations yield the normals as follows. Since the normal vectors are not scalar multiples of each other, the normals are not parallel, so neither are the planes. Taking the dot product of these vectors, we have Since the dot product is zero, the normal vectors are orthogonal, so the corresponding planes are perpendicular. The procedure to solve part C is the same. We find the normal vectors first. Since the normal vectors are not scalar multiples of each other, and the dot product is not zero, we conclude that the normal vectors are not parallel, so neither are the planes. The angle between them is given by the formula above. Let's see now how to find the line of intersection of two planes. Now suppose we were looking at two planes with normal vectors n1 and n2. If these planes are not parallel, then they intersect. But instead of intersecting at a single point, the set of points where they intersect form a line. Now we observe that since the line lies in both planes, it is perpendicular to both of the normal vectors. Thus, a vector v parallel to line is given by the cross product between n1 and n2. Let's summarize our findings. Any two non-parallel planes with normal vectors n1 and n2 will intersect, and the set of points where they intersect form a line. The vector v parallel to line is given by the cross product between n1 and n2. Let's see how it works. Find symmetric equations for the line of intersection of the two planes. We should remember that to write an equation for a line, we need two things: a point on the line and a direction vector. A vector direction v parallel to line is given by the cross product between the normal vectors to the planes. We need to find a point P that is on the line and consequently on both planes. A quick trick to narrow down the possibilities is to set the value of one of the variables. For instance, we can find the point where the lines intersects the xy plane by setting z equals 0 in the equations of both planes, and then we are looking for a point satisfying both equations. Solving the first equation for x and then plugging this x into the second equation gives us the value of y and the value of x. We see that point P is a point on both planes. So we have a point on the line and a direction vector for the line. So a parametric equation for the line is given by. Now let's address the problem of finding the distance between a point and a plane. Consider the plane and its normal vector n. Let P0 be any point in the given plane, and let Q be any point not in the plane. Drawing the vector PQ, we obtain a right triangle. From figure, we can see that the distance d from Q, the plane, is equal to the absolute value of the scalar projection, the vector PQ, onto the normal vector. Since point P lies in the plane, its coordinates satisfy the equation of the plane, and so we have thus the formula for can be written as follows. In short, the distance from point Q to the plane is the length of the vector projection of PQ along the normal n-to plane, where point P is any point on the plane. Let's summarize our findings. Suppose a plane with normal vector n passes through point Q. The distance d from the plane to a point P not in the plane is given by. Let's see how it works. Find the distance between the point Q and the plane. We begin by rewriting the equation of the given plane as follows. The coefficients of the plane's equation provide the values of a, b, c, and d. Substituting these values and the coordinates of the given point in the formula for the distance between a point and a plane produces the distance we are asked for. First, we find the normal vectors to the planes. The coefficients of the plane's equation provide the normal vector for the planes. We can see these two vectors are scalar multiples of each other. The normal vectors are parallel, so the planes are parallel. To find the distance between the planes, we choose any point on one plane and calculate its distance to the other plane. Any point will work. So if we put z equals y equals 0 in the equation of the first plane, we obtain the point with coordinates 3, 0, 0 in this plane. Then, from the second plane, we can determine that the values of a, b, c, and d, and we now plug these values into the formula above and find the distance between these planes. This last example is the most complicated. I will make a figure so that the solution is clearer. The figure on the side illustrates this problem. Since the two lines are skewed, they can be viewed as lying on two parallel planes. The distance between line 1 and line 2 is the same as the distance between their planes, which can be computed as in the previous example. So we begin rewriting the equations of these lines in the parametric form, and then we take their direction vectors. The common normal vector to both planes must be orthogonal to both direction vectors. So a normal vector is obtained by using the cross product between them. Now we need an equation for a plane. And since we already have the normal vector to the given planes, we must find a point that lies in one of the planes. Let's write an equation for plane 2. Since line 2 lies in plane 2, we can find a point in plane 2 by finding a point on the line 2. We can do this by substituting any convenient value of t in the parametric equations of line 2. The simplest choice is t equals 0, which yields the point Q. Now we use the point Q and the normal vector to write an equation for the plane 2. Now we need a point in plane 1. Since line 1 lies in plane 1, we can find a point in plane 1 by finding a point on the line 1. If we put t equals 0 in the equations of line 1, we get the point P on line 1. So the distance between line 1 and line 2 is the same as the distance from point P to plane 2.